Today we're going to be demonstrating the Introduction to Spectroscopy lab. The objective of this lab is to find two unknown concentrations of copper nitrate solution based on their absorbance.
In order to do this, we must first determine the peak wavelength of absorbance for this solution. This is done using spectroscopy. Spectroscopy is the field of science that has to do with absorption, emission, and scattering of electromagnetic radiation. For the purposes of this lab, we're going to focus on absorption. A UV-VIS spectrophotometer is a machine designed to measure the absorption of light that a solution has, a technique known as colorimetric analysis.
Beer's law demonstrates the relationship between the absorbance and concentration of a substance. It is written as the equation capital A equals A times B times C, in which capital A is absorbance, A is the absorptivity of a certain solution, B is the path length of the cuvette in the spectrophotometer, and C is concentration.
There are two parts to this lab, the first of which is determining the optimum wavelength for measuring absorption of copper nitrate. The only way to do this is to test a variety of wavelengths and use the data produced to determine which is best. Set the wavelength on the spectrophotometer to 360, making sure the switch on the bottom left of the spectrophotometer is on the correct range. You then first zero the spectrophotometer by placing a cuvette filled with deionized water into it. Make sure to remove all fingerprints with a chem wipe prior to inserting the cuvette. Set the transmittance to 100% using the knob on the right.
Be sure that the line on the cuvette lines up with the line on the spectrophotometer. Change the mode to absorbance with the button farthest left, and then replace the water in the spectrophotometer with a 0.1 molar solution of copper nitrate. Record the absorbance and repeat these steps for every wavelength up to 900 nanometers, increasing the wavelength by intervals of 20. It is important to zero the machine before testing each wavelength, and to always wipe the cuvettes with the chem wipe before placing them into the spectrophotometer. Also make sure to move the switch on the bottom left of the machine when the appropriate wavelength is reached.
Now we find the ideal wavelength by plotting absorbance versus wavelength and finding the peak of this graph. This point is the wavelength at which the absorbance is the highest. Now we move on to the second part of the lab, determining the unknown concentrations of two different solutions of copper nitrate. First, you must do the calculations behind creating 6 different known concentrations. The equation M1 times V1 equals M2 times V2 allows us to determine 5 additional concentrations using the 0.1 molar solution. In this case, 10 milliliters of water will be placed in each beaker, and then 10 milliliters of the prior concentration will be added to each beaker. For example, 10 milliliters of the 0.1 molar solution will be placed into beaker 2, making a 0.05 molar solution. 10 milliliters of the 0.05 molar solution will be placed into beaker 3, and so on.
Using the peak wavelength that was determined earlier, we will now determine the absorbance of each known concentration at that wavelength, as well as the two unknown concentrations. Don't forget to zero the spectrophotometer and use a chem wipe on the cuvettes. Using the data recorded from this, we can now create a linear plot of absorbance versus concentration using the known concentrations. This is known as a Beer's law plot. Make sure to record the equation for the best fit line as well as the r-squared value for this graph. Looking back at Beer's law, capital A equals A times B times C, we can see that A and B did not change in this experiment, allowing us to combine those into a constant K. We now have the equation of a line y equals mx plus b, in which y is absorbance, m is K, x is concentration, and b is 0. Since our Beer's law plot gives us m and we have the absorbance of the unknowns, we can plug those in to yield the concentration for the unknowns. Beer's law states that there is a direct linear relationship between concentration and absorbance. Another property of a Beer's law plot is that it should pass directly through the origin, because when concentration is equal to 0, so is absorbance. The r-squared value on our Beer's law plot demonstrates how well our points correlate linearly. With an r-squared value of 0.9999 and a y-intercept value of negative 0.0007, it is clear that our data does adhere to Beer's law and our unknown concentrations are accurate.
The largest room for error in this lab is fingerprints on the cuvettes. Fingerprints leave a residue on the cuvette that absorbs light. This causes the absorbance read by the spectrophotometer to be higher than the solution's absorbance truly is. In order to minimize error, it is important that each cuvette is thoroughly rubbed with a Kim wipe before being inserted into the spectrophotometer to remove any remaining fingerprints.